Good morning and welcome to Physical Science. Today we're going to talk about changing states, and I was just wondering, can you guys name some of the changing states? And which one is the cat undergoing in the GIF? Good morning, Alexis. So the cat here is starting out as a solid, and then he puts himself in the bowl and turns into a liquid. So what's that called when you change from a solid to a liquid? Exactly. The cat is melting. What's the opposite of melting? Yeah, freezing. All right, so there's two of our change of states. Can you think of some more? Yeah, we've got boiling. And there's some synonyms for boiling, like evaporating is a synonym for boiling. Altogether, that is called vaporization. And the opposite of vaporization is condensation. Thank you, Maya. And so that's four of them. There are two more. What if you skip over the whole liquid phase and you just go from being a solid to being a gas? Starts with an S. I'll just give it to you. It's all right. I wouldn't have expected you all to hear this before, but when you go directly from a solid into a gas, that's called sublimation. And if you go directly from a gas right into a solid, that's called deposition, like it got deposited. So couple new vocabulary words for today. And I am going to move along here. So we are a couple minutes into class. So just a reminder to make sure you are attending and participating. You guys are great at attending. Some of us could participate a little bit more in class though. And good morning, Nigel. Remember to keep chat box conversation limited to the content of the lesson. Be respectful and courteous. And you guys do really, really well at the code of conduct. Good morning, Isaac. All right, so I got an email with our schedule. Have you all seen the schedule for next week? Okay, so instead of having the review sheet done before Friday this week and going over it on Friday, we're going to have work time on Friday. You can take the review sheet as a practice test in class on Friday. I would like you to sit down with them as a practice test so that you get used to answering questions in that testing environment. And then you really get to find out what you know and what you don't know, and you can focus your studying onto those items that you didn't know. Then next week, we're going to have one block session for review. So we'll either have an hour and a half or an hour and 15 minutes next week to go over the correct answers on that review sheet and then give you some time to do some review activities. There'll be one for testing, and all of you guys will be coming to the live testing for physical science. And then there'll be one session for makeup. So you either have to take your IA in the regular testing session, that would be best, or in the makeup session. And there's the schedule. If you want a copy of the schedule, it's right down there in the images. And the best way, if you wanted to download it, in the images, you can just look at it. But if you want to download it, go to the whiteboard down here. There's three little horizontal lines in the upper left-hand corner. and you click on those and click on my attachments. And then anything that I've released you can download them straight from just clicking on them there. So let's see, for period 4, we're not going to meet on Monday. We're not going to meet on Tuesday. We will meet, goodness, we have the last review. Our review is on Thursday and at the same time. And then our testing period is on Friday. And our makeup testing period is on Friday afternoon. So make sure that you are available for class on Friday. That we've got to take that interim during class. And this is 4th period. I believe everyone is testing during class. If you're not, I'll send you out an email. And good morning, Maya. And good morning, Jordan and Dakota. How are you? And hello, Anna M. So we have a knowledge check. So using those emojis that are down here in that corner, please see what you can do with this question about volume related to temperature of a gas. All right, so I need some more answers. So thank you to Amanda, Isaac, Jordan, Kessler, and Rukaya for answering the question. And thank you, Anna M. But I'm still waiting for answers from Alexis, Dakota, Jalen, Juliet, Kate. Thank you, Kate, Maya, and Nigel. And remember, if you don't know what's going on, you want some help, I have the red X for you. So you can always participate, even if you're unsure. And I am more than happy to see a whole bunch of red X's. I'd much rather see that than blanks, okay? Because blanks, I have no idea if you get this or not. And so I don't know what depths to go into when I talk about the question. If you give me a red X, then I'll spend some additional time going over it. I'll go over these until you understand them. Okay, I'm going to annotate so we can see. Let's look here. And nobody picked the smiley face. Let me see. I'll go with light green today, lime green. So nobody picked smiley face. That's good, which means they are independent of each other. That means that one went up and the other one stayed the same, or one went up and down and the other one did, something. It's hard to do totally different things with my hands. So we can definitely say that one is out. And now look here at the volume, right? Our volume is going up. What's our temperature doing? What's the temperature doing? It's going up too, right? They're both increasing. We get this increasing line, and since they both are going up together, that is the definition of a direct proportion. So that is our correct answer. If it was inversely related, then it would have more of a downhill. That would be inversely related. It would be a downhill slope because they would be going in opposite directions. And we don't have negative correlations in science, or not in physical science. That would be more of a math thing. So once you understand why that's the right answer, it's good to change your emoji. And good morning, Cameron. If you weren't participating before, but now you get it, go ahead and give me that OK symbol. Good morning, Isaiah. Good morning, Leilani. Leilani, I know that you can't give me emojis, so no worries about that. I'll try not to call you out about it. I did turn in a little ticket about that, and I sent you an email, Cameron, you too, right? I sent you guys an email for you to give me a screenshot. So if you would take a screenshot of your lack of emojis while we're in class today and email it to me, then we can get that fixed. All right, I'm going to unannotate, and we are skipping. I'm going to skip here real quick and talk about the definition of temperature, because you need to know what temperature is for our second check your knowledge question. So temperature is the average kinetic energy of the particles in the system. So if you have a solid, say you have a solid, the particles are vibrating, they're connected together, right? And so they're always vibrating a little bit as long as you are above absolute zero, right? And so if you heat it up, they vibrate more, but they're still connected, right? And then once it melts, it's gonna come apart, and they're still gonna be vibrating. As if you heat it up more, they'll vibrate more, right? And slide across each other. So as you increase the temperature, the average kinetic energy of the particles is gonna go up too. So if you've heard of this definition of temperature before, can you give me a green check? This might be new. Okay, yeah, some of you guys have heard of this before. Yeah, and most of you guys are juniors, seniors, some sophomores, so we should be good with that. So based on that, I'm gonna go back to our other question. So here is our knowledge check number 2. I'll give you a minute. Let me clear the responses. All right, go ahead. I'll be quiet. All right, I need some more participation. Let's see if we can eliminate an answer here. So you guys that chose answers already, what was the easiest one for you guys to eliminate? The OK symbol, let's look at that one. With the OK symbol, decreasing the temperature, right? Because it wants the average kinetic energy to increase, right? And we want the volume also to increase. So if you make it colder, then the average kinetic energy is not going to go up. It's going to go down. So we can definitely get rid of OK. And then smiley face, we can get rid of that one too. If we lower the number of gas molecules inside the container, we take some gas out, that's going to decrease the pressure, right? So to keep a constant pressure, it's going to have to shrink, and the volume would go down. And so that's why smiley face is out. So it's really just between loudspeaker and turtle. And good morning, Sanad and Miranda. How are you guys? So loudspeaker or turtle. Can I get some more participation here? Or red X, that's always out there. And good morning, Jacob. All right, so let's see. If you increase the Kelvin temperature of the gas, you heat up a gas and you want the pressure to be stable, you think about that simulation we did on Tuesday where you heated up the gas and it got bigger. You can also think about like a balloon that's got a constant pressure relatively. If you heat up that balloon, you know, it will expand. I have a list of some other things you can think about. The tires on your car, a pressure cooker. That one would be a constant volume, though, with the pressure cooker. You can think about your tires, too. They're going to, as you heat them up, it's going to increase the volume a little bit. Soccer ball would be another good one to think about with these. So, yes, if you increase the temperature, it's going to increase the volume, and it will also increase the kinetic energy. So that is the correct answer, is the loudspeaker. But I want to go over why the turtle is not the right answer. Because if you put more particles into your container, it's going to increase the volume. But if you don't add any heat to it, it's not going to change the temperature. And so that was the problem with that one. So the temperature stays the same. So I don't see turtles changing over to loudspeakers. And so if you have questions, I need you to ask those or give me a red X or something so I know that you are good to go or not good to go. Okay, thank you. Appreciate it. We've got to do that communicating. Teaching is going to be most valuable and learning is going to be most valuable to you if I know where you are and what you need. All right, so today we are going to talk about changing states of matter, and we're going to analyze and interpret data to explain the flow of energy when you're changing states. And we're going to have to look at some heating and cooling curves. I love graphs because I find it makes it easier to understand things when you can read it off the graph. However, these heating and cooling curves are not in Canvas. Oh, good job, Alexis. So I'm going to give you time first to go through the change of state lesson, about 15 minutes. And if you need any help with anything, you just stay right here and I'll help you. And if you want to go work on the lesson, you can give me that green check and I will put you in the quiet breakout room. Then we'll come back and I'll talk about what a heating curve is. And I've got some practice, I've got a demo, we got lots of good stuff. And then we'll end by playing a quizzes, and you can either work on your own with that or you can compete against me. I made some silly mistakes when I took that one because I was trying to do it fast. And so that's never a good thing. But anyway, I'll put you all in the quiet breakout room if you have a green check. All right, welcome back from your lesson work time. What questions do you have about it? All right, I'm guessing that means there are no questions. Can I get a green check if you're all good with the lesson? That way I know you're back here with me too. Excellent. Thank you, Anna and Alexis. Thanks, Jalen and Jordan. Thank you, Rukaya. Thank you, Kessler. Thank you, Jacob. Oh, thank you, Leilani. I was just looking for a check to see if you had any questions or if you were good with the lesson and you are back with me. So appreciate it. I'll check private messages in just a minute. So I want to take a look at, and thanks, Miranda. Take a look at these phase changes, which phase changes and state changes are the same thing. So these are not in the Canvas lesson. So I'm going to explain a little bit how these look. And I'd like to annotate on here. So we've got our temperature, which is always going to be on the y-axis and always goes up. Heat energy or time sometimes is on the x-axis, and it always increases as you go across. We always start down low with the solid. You might start with the liquid phase too, but generally it's always the solid. And you can see the nice orderly arrangement. And as we are adding heat energy, the temperature is going up. That's a nice direct relationship. And since the temperature is going up, do you think that's kinetic energy or potential energy that's increasing? When the temperature is rising, is that potential or kinetic energy increasing? And who's going to agree or disagree with Rukaya? Come on, I would love to have 20 responses here. Think about that definition of temperature with Gumby there. Was it kinetic or potential energy? All right, thank you, Isaac and Alexis, for agreeing. And yes, that is kinetic energy. So I'm going to put a K on there. For some reason this doesn't stay very well. Wish it would write a little darker, but I'll go with that K on there. So where else do we see the kinetic energy increasing? So while it's boiling here, you can see it's got a horizontal line, right? So that's telling us, if we follow that over, that it's staying at the same temperature. And so while it's boiling, the temperature isn't increasing, so there is no increase in kinetic energy. What's actually happening while it's boiling is it's increasing in its potential energy. Because what's happening, I'll put a P on there, what's happening while it's boiling, it's changing from moving at a certain rate as a liquid to moving at that same rate as a gas. So the particles are moving at the same speed, which is their kinetic energy, but they're more disconnected and separated from each other, so they have more potential energy. So where do you think we would find more kinetic energy? Which step? What step looks kind of like that solid where you've got increasing temperature and increasing kinetic energy? Yeah, when the liquid is warming and when the gas is warming. Anytime you are warming or cooling, then your kinetic energy is changing. So we'll put a K there and a K up there. And they're so light. I hate that they're so light. And then, so what's going to go during freezing and melting? Is that going to be a change in kinetic energy or a change in potential energy? So when it freezes and melts, is that going to be a change in kinetic or a change in potential energy? And yeah, thanks Miranda for agreeing with Rukaya. Anyone else want to agree or disagree? Thank you, Jordan. And guys, I will say that the more you participate in class, the better understanding you're going to walk out of here with. And I want you to have a really strong understanding of all of this. Okay, so that's going to be a change in potential energy while it's freezing or melting. So basically, you've got some solid particles and they're vibrating, right? And they're going to keep vibrating at that same rate, except they're going to separate and then they can slide past each other, right? So that's what happens when you go from a solid to a liquid. You keep the same temperature, the same kinetic energy, but their movement changes and that changes their potential energy. Same thing happens when it freezes. They're moving at the same quickness, they're just connected together. So heating curve is going up, cooling curve is when you follow the line or the graph back down. So what questions do you have about this heating curve or phase change diagram? Okay, so see, that was a good sign. Someone gave me a red X, which means I don't get it. So I'm going to show you something else that hopefully will allow you to get it. And if it doesn't work, then I'll show you something else. And we can keep going over this until it works. But this is a demo. Oh, I'm going to put this in the chat. So if you want to do this on your own rather than watching it on my screen, then you can do that. And if you are going to watch this on your own and not participate in here, then just give me a green check so that I know that you are doing this on your own. And then I won't expect you to be typing in the chat. Okay, so but you can still listen and I'll kind of walk you through here. So the question is, does the temperature of water rise while it's boiling? All right, so here's my interactive. It's got one of the heating curves up here. And so this is going to show you visually what's happening with the water and connect it to what's going on with the curve. And you can see we have a flat point in the curve at 0 degrees Celsius. That's the freezing point of water. And we have another flat line at 100 degrees Celsius. That's the boiling point of water. And I'm going to start from a solid first and turn it into a gas. And that way we have our heating curve. All right, so you can see the little particles in there and they're vibrating. I don't know if you can see that, but if you look really close, you can see them vibrating, especially if you have it full screen at home. Maybe I should try putting this on full screen. And then I could, you can turn off my camera or minimize me I can see them a little bit on my screen, vibrating. Okay, so I'm gonna play. And so right now it's heating it up as a solid. You can see the temperature is in the upper right-hand corner. I paused it. So now you can see when it gets to 0, it's gonna start to melt, and it's staying at 0 degrees. This is because the energy that you're putting in is going to pull the molecules apart and melt them rather than cause any temperature rise. So here we are changing the potential energy of the system. And I'll let that keep going. And so they're all moving at the same average kinetic energy. The temperature is the same. They're gaining potential. Now when it's all liquid, the energy you're putting in goes to heat them up, and you can see that they are moving faster and faster. And occasionally you get a little gas particle where a molecule is headed towards the surface and it pops right out. You can see that the temperature is increasing. It's going to increase until we get to 100 degrees, where the water will start to boil. And it has started to boil and steam. You can see the steam now. The level of the water is going down, and the temperature is holding because now we're just gaining potential energy. The particles are spreading out further and further apart. And once they've all become a gas, and they're bouncing around, then our temperature will start to rise again. Oh, good, Jordan. I really like this one too. Okay, so that's our heating curve. So, good, I'm glad you liked it, Amanda. So what questions do you have about it now? And let me check, see if there's any more red X's or if they have disappeared. If you have a question or you don't understand, you can give me a red X. If you're good, you can give me a green check. I'm gonna switch this around now and go from a gas down to a solid. So it has put it into the freezer. And let's see what happens now. It's gonna start at 150 degrees. And they put a lid on it to keep that gas inside the container. And so once it hits 100 degrees, you can see it started to condense and form a liquid. So they're not moving any slower, but they have lost energy, so the particles are just closer together. They're more clumped together. And so more and more, well, it's all turned into a liquid now. And so once it's all liquid, then the temperature will start to drop as we remove heat from the system. And once we hit 0 degrees, then it's going to start to freeze. You can see the particles slowing down. It's losing kinetic energy, and boom, now it's only going to lose potential, and they're forming those ice crystals. And then once that's all ice, then it cools down more and the particles vibrate less and less and less. Oh, good. And that link is in the chat. I believe the link is also in the Explore and Do More, so you can always find that. Good question, Rukaya. Yes, at absolute 0, they stop vibrating. So negative 273 degrees Celsius. Really, really cold. Okay, so we did that. All right, I have a practice for you. I'm gonna put this on the whiteboard. Wait a sec, what's the problem? Oh, there's no whiteboard present. Hang on. Haha, I was under my attachments. Okay, I'm gonna copy this to the whiteboard and give you guys the ability to fill in these blanks, and let's see what you know. So you should be able to write on the screen. Use that little A with the dotted box around it. So we're just filling in the blank boxes. We've got solid. Melting. Gas. All right, we've got two more. So in the chat, tell us how you think you guys are doing. We've got cooling. So give them some feedback. Does it look good? Any idea what that last box might be? Anything need to be fixed? Or is it all good? So we've got heating and cooling. Just wondering if you guys can hear me. Okay, Amanda, you said that we're doing good. Okay, good, good, good. Because yesterday I was having some issues with my voice and camera just going out completely for everyone. So the heating is correct, but it doesn't actually go in the box that is heating, but I was looking for a specific change of state to go in the box. And same thing with cooling. Cooling is correct, but it's not the change of state that goes in there. All right, there we go. Boiling works. And which one is going to be opposite of the boiling? Oh, freezing. Freezing's down at the bottom there. It goes with melting. And boiling and vaporization is with condensation. All right. Excellent, excellent. Questions about heating and cooling curves? Any red X's, or are we good? Green checks? Hey, got another green check. All right, so there's another one. Thank you. I had a lot from before, but a few more are good. So there's our answers. And guys, these the PowerPoint is also available by clicking on your attachments on the whiteboard. So what though happens if you skip the liquid phase? Have any of you ever played with dry ice? Any experienced dry ice? So we've got a solid. You can see the little square there. That goes directly to a gas, no liquid phase. So no one has ever experienced dry ice? You have to be careful with it. See, he's got these big, heavy gloves on, but it is a lot of fun. Okay, so I'm going to show the video at the very end, and Rukaya, you said you saw it at the science fair. As you're leaving, I'll show you the video if you want to watch it or not. But this is the sublimation and deposition part of the phase changes. So I want to see if we can answer some questions without liquid on one of these diagrams. So in what state is it between A and B? Right, this is going to be a solid at the beginning. And then up here in C and D, what did it turn directly into? Into a gas, right. So it starts as a solid and it ends as a gas. So in the middle, during B and C, what two states is the carbon dioxide in? So while it's sublimating and depositing, it's in two states. What if we skip the liquid phase, though? We're skipping out liquid, so it's gas. And what's our other one? So in the middle here, it'll be both a gas and what other state? Yeah, solid. So as it's sublimating, you can see that it's both in the solid form there and in the gaseous form. And the reason that this is slightly dangerous is because it's so cold. If you were to hold that in your hand, it could cause a freezer burn to your skin. And so that is the main problem with it. Also, you want to be real careful if you ever have any dry ice to keep it outdoors. One time I put the cooler with dry ice in my car overnight so then I wouldn't forget to take it with me to school. My entire car filled up with carbon dioxide and there was no air to breathe in there. So I had to roll down my windows and let the car air out before I left. So I'll never do that again. You leave it outside completely. Yeah, anytime you breathe out, what you're doing is like in the winter, the warm air comes out of your mouth and it causes the moisture, the water and the air to condense into little droplets. And that's the same thing happening with the dry ice. When it sublimates, it turns into a gas, it cools the air down, just like your breath was getting cooled down, and that causes the water to condense. So this fuzz that you see, the smoke that you see, is actually water droplet that are there. You're not actually seeing the carbon dioxide, you're seeing water droplets. But it's there because the CO2 has cooled it down. Carbon dioxide is odorless and colorless. Do not eat dry ice, really bad. It can burn, it would freezer burn the inside of your mouth. Anyway, so during B and C, is that kinetic energy or potential energy being gained? Oh, okay, I don't know what dragon breath is then. Yes, potential energy is being gained there in the middle. Awesome. Questions about CO2 and sublimation? Any red X's to give me? Oh, a green check. I like green checks. We're almost all a green check. That is good. Okay, our last thing to do is to check your knowledge. Another green check. Awesome. So you can either play with the quiz link on the board. That you can turn the timer off for that one. Or, oh, I forgot to open this up this morning. Or you can play against me and try to beat me. Let me get to my quizzes real quick. And again, if you want to play against me, you go to the join.quizzes.com that's in the chat and put in that number 143024. And then you can play against me and everyone else who played yesterday. And if you would like to go back to the quiet workroom to do this, you certainly can. Just give me a green check. You're welcome to stay here if you want to interact with each other. And yes. If you want to stay here, ask questions, interact, then stay here. Otherwise, give me a green check. I'll put you in the quiet breakout room to do the quizzes per person. So I would like to see everyone add one item in either side. With or without your name is fine. And if you do not have board tools, please let me know in the chat so we can get that fixed up. And if you don't have board tools, also send me a screenshot where they aren't there. Okay, so when you have volume change with cooling, when you cool something down, the particles slow down and they're moving. And when the particles slow down, and then what's going to happen is the volume is going to get smaller too. And that's when the pressure is the same. Because pressure is when the particles hit the walls. And so if you cool it down, they're going to hit the walls less. So in order to equalize the pressure, it's going to shrink. You could test this. If you have a little balloon, one of those small ones, you could measure the diameter of it, put it in your freezer for 10 minutes, pull it out, measure the diameter. And maybe I could even do that in class tomorrow. I'll think about it because I think my daughter has some little tiny balloons. Excellent. Well, we are getting close. We have 1 minute left in class. The volume shrinks. So it will never go down to 0 because there will always be particles in there, but the volume will go down. Okay. Cool. So I wanted to show you this little video on the way out. You're welcome to stay and watch. If you have another class, you are welcome to go to your class. But let me make this big so you can watch it. And then I will see you guys tomorrow for our work day. And we will work on the review sheet tomorrow. I will answer any questions that you have about anything tomorrow. And I'll see you all tomorrow. All right, and there you have it. Some cool dry ice tricks. Yeah, if I could have, I would have had some dry ice. They used to sell it at Kroger right down the street, but it's been gone from there for years. So I think you have to go to like Bass Pro Shop or someplace like that. Someplace really big. Maybe Sam's sells it. I don't know. Anyway, yeah, great question about, you put that in your in punch at a party so that you have Halloween's, you have the mist all going everywhere, and that is perfectly safe to drink. Dry ice sinks, so so you're not going to get it in your cup, that kind of thing. Or if you're drinking out of a cup and it's in the bottom, that's perfectly fine. Yeah, the CO2, carbon dioxide's in all your carbonated beverages. So if you have a soda, you're drinking CO2 right there. So thanks for coming in, guys, and I will see you all tomorrow. Have a great afternoon.